In all honesty, section 310 is not very lengthy. Okay, there's only a couple of slides here, and I kind of decided not to do two of them anyway. So it's really not much material. So what is section 310? Section 310 is called linear approximations and differentials. Again, I hope we know that the derivative is really just the difference between where I'm going to and where I'm at, like in terms of a point, and finding the slope at that point and getting closer and closer to the slope. That's kind of like where we started, right? That we're going to use that same idea in terms of differentials. But what we're first going to start out is we're going to talk about linear approximations. Now, we've seen that a curve lies very close to its tangent line near the point of tangency. In fact, if we zoom in toward a point on the graph of a differentiable function, we notice that the graph looks more and more and more linear the more we zoom in. Okay? If we zoomed in and zoomed in and zoomed in and zoomed in and zoomed in to like an exponential function, even though we know it curves, but we looked at a point and we said, okay, at whatever, 3, 1 or whatever it may be, and I zoom in and I zoom in and I zoom in and I zoom in and I go as far as I can, the function stops looking exponential and starts looking linear. That could be any equation. That could be any polynomial or quadratic or whatever we may have. Logarithmic, exponential. If we zoom in on any function, it will start to look linear. No matter what, where, doesn't matter. This observation is the basis for a method of finding the approximate values of a function. The idea is that it might be easy to calculate a value, f of a, of a function, but difficult or maybe even impossible to compute nearby values. Maybe they're undefined. Maybe they're very difficult to calculate. So we settle for the easily computed value of the linear function L, whose graph is the tangent line. Now, do we know already how to calculate the equation of a tangent line? Yes, that's using the derivative. We find the slope, we get the point, we plug it into point slope, and we solve for y. The difficult piece to that is getting the slope. We find the derivative and plug it in to find that slope. That's basically what's called a linear approximation of that function. And that's what we have down here. And that's actually what you have at the very bottom of your formula sheet that I gave you, your derivatives cheat sheet. That very bottom box is actually what's called the linear approximation formula. It's the linear approximation formula. Honestly, you don't really need this. You don't really need this. You've done this a million times already. What is this actually telling you? It's telling you that any function, you can have f of a plus f prime of a times x minus a, and that will give you the value of the linearization, the linear approximation of that function. Like, think about it this way. If I had the function, and I think I wrote it in here. Oh, no, I didn't. That's okay. If you had the function, think about it as y minus y. If you had the point slope, y minus y1 is equal to mx minus x1. Think about what we've got there. What we have here is this is my derivative, f prime at a. And if it's f prime at a, well, then that x value is a. Right? Then what's the y value? F of a. So y minus f of a. That is really what we've been doing all along when I ask you to evaluate the equation of the tangent line. You find f prime, you plug in a, you plug in a into the x minus x1 into point slope, and you plug in the y value, whatever it may be, f of a, into the y1 value. And then you solve for y. So add that f of a over to the other side, we would have f of a plus f prime of a times x minus a. People, pay attention. So we have f of a plus f prime of a times x minus a. That is really the linear approximation formula. We don't even really need that. But it's there for us if we need it. It's just a simpler way to write it. F of x, they call it L of x for linear approximation. L of x is equal to f of a plus f prime of a times x minus a. And again, I have to tell you what a is. I have to tell you where you're approximating it at. Let me show you what I mean. And again, it's got two different names to it. You could call it the linear approximation. I guess three different names. You call it the linear approximation or the tangent line approximation, or what's called the linearization at A. All three of those things kind of are synonymous. They're synonyms. All right, so find the linearization of the function at 1. Let's start there. Let's find the linearization. Again, the directions could have told you to find the linear approximation. The tangent line approximation. That's really saying the exact same thing. But we'll be fancy and call it the linearization. At 1. And again, I always have to tell you where. At 1. Okay, so remember that the linear approximation formula is L of x is equal to f of a plus f prime at a times x minus a. So we have to find all of these things. Well, let's start with f of a. So what is f of 1 in this case? Well, that would be the square root of 1 plus 3, which is 4, which is 2. So f of 1 is 2. That's like the coordinate, right? 1 comma 2. So we would need to now find the f prime at a. Well, let's find f prime of x and then evaluate it at a. Okay, well, this is just x plus 3 to the 1/2 power. That is f of x. So now when we take f prime, that is 1/2 x plus 3 to the negative 1/2. Do I need to do a chain rule here? It looks like I might, but what would be the derivative of the inside? 1. So does it really matter? No. Now, if this had been like an x squared plus 3, then it would matter, but it's not, so we don't. So this is a 1 over 2 square root x plus 3. That's f prime x. Again, I shifted it to the denominator because of the negative exponent. The 2 from the fraction, 1/2, goes in front of the square root. Okay, so let's find f prime of a. F prime of 1. 1 over 2 square root 1 plus 3, which is 1 over 2 square root 4. 1 over 2 times 2 is 1/4. That's my slope. I would choose home alone. Just saying. So L of x is equal to f of a, which is 2, plus f prime of a, which is 1/4, and then x minus a. A is 1. And now we just solve. We just simplify it. So we take L of x is equal to 2 plus 1/4 x minus 1/4. So 2 minus 1/4 L of x is equal to 1.75. Did I really do the decimal? Yeah, I did a decimal. 1.75 plus 1/4 x. That is what's called the linearization at 1. The linear approximation at 1. The tangent line at 1. Now, that's not where this problem stops, though. This problem says, okay, use that linear approximation to approximate the values of the square root of 3.98 and the square root of 4.05. Now, is this going to be the exact value of the square root of 3.98 and the square root of 4.05? No. Because this is the linear approximation at 1. This is the linear approximation at 1. So it's going to be a little bit off. Let's see if they're underestimations or overestimations as well. So when I say, okay, I want the square root of 3.98, what's my x value if I have 3.98? Well, think about this original one. I'm saying this. The square root of x plus 3 is the square root of 3.98. Okay, pop off the square roots. X plus 3 is equal to 3.98. So x is equal to 0.98. Oh, so x is really close to 1 here, right? The x value for this case is very close to 1. So our number is actually going to be really close. Our value, our linear approximation, is actually going to be really close to the actual value. But again, it's not going to be right on. So if x is 0.98, well, then I'm saying 3.9 square root of 3.98 is equal to 1.75 plus 1/4 of 0.98. Because that was my equation, right? 1.75 plus 1/4 times x. Well, in this case, my x is 0.98. Well, let's see what this linear approximation estimates that value to be. We got 1.75 plus 0.25 times 0.98. I get 1.995. Square root of 3.98 is approximately 1.995. Let's see what the actual value is. Square root of 3.98. Wow, we were really close, weren't we? So we used some value. Now, this is a case where this is futile, because would we ever really use an approximation for this value? No, you'd probably just plug it in your calculator and do square root 3.98, see what it actually is. But I'm telling you, you can do this for functions that is not easily differentiable, or not easily finding the values around it. Okay, or maybe those values aren't defined, something like that. And then let's do one more. Let's say square root of 4.05. Okay, so the square root of x plus 3 now is equivalent to the square root of 4.05. Okay, pop off the absolute values. Square roots, we get x plus 3 is equal to 4.05. Subtract the 3, x is equal to 1.05. Again, something very close to 1. So our approximations should be very good. Our estimations should be very good because it is close to 1. So the square root of 4.05 is going to be equal to 1.75 plus 1/4 of 1.05. That's our x value in this case. Let's see what it comes out to be. 1.75 plus 1/4 of 1.05, which gets us 2.0125. Square root of 4.05 is 2.0125. Now, I'd like to see how close that value actually is. So if I square root 4.05, let's see how close I actually get to it. Yeah, I mean, I'm within a rounding error to the nearest 100th, 10th, 100th, 10,000th place, right? That's a rounding error. That's very close, right? Now, it all depends on what you're working with. It all depends on how much your error you can stand. You know, if you needed to be more precise than that, well, then this wouldn't be a good approximation. You know, it all kind of depends. What's your error tolerance? Okay. So that's the linear approximation. Now, what will I be asking you to do? Mainly find linear approximations. Usually, I'll be asking you to stop right there. What is the linear approximation at point this or at point that? That's where I'll be asking you to stop. But what is this used for? It's used to calculate values that are not so easily calculatable. Made that word up. The book gives this description of how it's used in physics, so I'll just talk through it a little bit. Linear approximations are often used in physics. In analyzing the consequences of an equation, a physicist sometimes needs to simplify a function by replacing it with its linear approximation. Okay, because we can simplify things if we put it into a simpler function. For instance, in deriving a formula for the period of a pendulum, physics textbooks obtain the expression a sub t is equal to negative g sine theta for tangential acceleration, and then replace sine theta by theta with the remark that sine theta is often very close to theta if it's not too big. So all you're getting from that is that they can replace a function with something a little bit more simple that might help you a little bit more along the way. So because they say sine x is pretty close to x at 0, around 0. So in effect, the derivation of the formula for the period of the pendulum uses the tangent line approximation for the sine function. Okay, so what they're doing here is they're actually just changing out the different function. Because it's the linearization, it's really close to it. Now, exact value? No, but it's just really close to it. Close enough that they can say, we don't care about the error away from those values. Just as long as you're using those comparable values, it's close enough to it. Okay, so let's talk a little bit more about those close enough values. This is where we get into these things called differentials. Differentials. The ideas behind linear approximations are sometimes formulated in the terminology and notation of what are called differentials. Now, differentials you have calculated before. You know what differentials are. Obviously, the root word of derivative and differentials are very close. If y is equal to f of x, where f is differentiable, then the differential dx is an independent variable. That is, dx can be given the value of any real number. The differential dy is then defined in terms of dx. Think about this. If I have dy is equal to f prime dx, understand the notation there. dy, differential on y. Isn't that, like, can't I replace that with delta y, differential on y, is equal to f prime differential on x? Okay, differential. Can't I replace that with delta x? Think about what would happen if I solve this equation for f prime. Delta y over delta x is equal to f prime of x. Hey, isn't that just slope? And isn't our derivative just equal to slope? So we have this differential equation where we can say dy is equal to f prime dx. dy is equal to f prime dx. That is our differential equation. So dy is the dependent variable. It depends on the value of x and dx. If dx is given a specific value and x is taken to be some specific number in the domain of f, then the numerical value of dy can be determined. Let me show you what I mean here. Compare the values of delta y and dy. If y is equal to f of x is equal to x to the third plus x squared minus 2x plus 1. And x changes from two different things. We're going to set up two different scenarios. The first scenario being going from 2 to 2.05, and the next scenario being 2 to 2.01. Okay, so let's start off here with A. So the first thing that we have to do is find f of 2. Because delta y, remember that delta y in the formula, delta y is kind of like f of 2.05 minus f of 2, right? That's the change in the y values. That's the change in the y values. So we need to find 2.05 and 2. So f of 2.05. Okay, let's plug it in and see. That we have 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. So we get 9.717625. 9.717625. Okay, what is f of 2? Well, f of 2 is a lot easier to calculate. 2 to the third is 8. I guess I'll do it in here. 8 plus 4 minus 2 times 2 is 4 plus 1. 9. Okay, so what is delta y then? 9.717625 minus 9. 0.717625. There's a reason why I'm going out to that many decimal places. So that's delta y. Now let's compute the value of dy. Now remember that dy is equal to f prime of x dx. Right? Delta y is equal to, excuse me, not delta. Dy is equal to f prime x dx. Now let's figure out what dy actually is. Well, dy is f prime x. So 3x squared plus 2x minus 2. Right? That's f prime x times dx. Now, where is this at? This is at 2, right? This is at 2, going from 2 to 2.05. So dy is equal to 3 times 2 squared plus 2 times 2 minus 2, and then multiplied by the differential on x. Well, what was the differential on x? 2 to 2.05. What's the differential on x? 0.05. Okay, let's evaluate that. So 3 times 2 squared plus 4 minus 2 times 0.05. 0.7. So dy is 0.7. How close were we? I mean, relatively close, right? Relatively close. So by using this differential equation, this dy is equal to f prime x dx, using this differential equation, we can get pretty close to the difference on the y values. Now, we were given an equation that it was really easy to do that with. The nice thing about this differential equation is that this applies to equations where it's not so easy to do that with. Where it's not so easy to just run the numbers and calculate, okay, what is it from 2 to 2.01 or 2 to 2.05? Let's do that same thing for part B there. Because it's the exact same thing, so let's run the numbers again. So f of 2.01, now that's a number that we need. I'll be a little cheater here and just go off my notes. It's 9.140701. And then f of 2, same thing, is 9. So the delta y in this case is 0.140701. Now let's calculate the differential using 2, but not at 0.05 anymore, but 0.01. So I've got dy is equal to that same 3x squared plus 2x minus 2 dx, but now the thing that's changed is my dx. It's the same value at 2. So dy is equal to 3 times 2 squared plus 2 times 2 minus 2, but now 0.01, because my new differential on x is not 2 to 2.05, it's 2 to 2.01. So let's run those numbers now. The nice thing is I got it right. Yeah. Oh, it was 14. Okay, 14 times 0.01. 0.14. dy is 0.14. Oops, 0.14. Now, we got even closer to that value now. We got even closer to that value. Want to know why we got closer to that value? Is because delta y got smaller. That's that same idea that we had when we were talking about delta epsilon values. Right? That's why they called it a delta value, because it was the change in your x value. if I make that x value smaller and smaller, yeah, no matter, the delta y is going to get closer and closer to dy. The actual change in the y values is going to get closer and closer to the linear approximation in those changes in the y values. Okay. All right, we will pick up tomorrow. Honestly, we have one word problem to do, and that's it tomorrow.
Yes. We just want to send that on over and appreciate it.
Yeah.